We are now ready to move on to the next stage of the architecture, the Upsample module. The role of this module is to enhance feature map resolution by applying a scale factor of 2, which increases the spatial dimensions of the input feature map. This enables finer spatial detail recovery, which is crucial for tasks like object detection. The module achieves this using the nearest interpolation method, which replicates pixel values, ensuring computational efficiency and simplicity. In fact, the scale factor and interpolation method are the only two parameters for this layer. We can run this quickly and observe that while the channel dimension remains unchanged, the height and width are both doubled. For example, if we compare the input and output of a small region within one of the channels, we can clearly see how a 2x2 feature area is scaled up to a 4x4 region, maintaining the original values but expanding spatially in both height and width. From here, the tensor progresses to the next layer in our architecture, the concatenation layer. This layer is defined as a class that internally calls torch.cat, with its primary argument specifying the dimension along which to concatenate. The concat module combines feature maps from multiple layers by stacking them along dimension 1, which corresponds to the channel dimension. This integration enables the model to merge features learned at different stages of the network, improving overall feature representation. In this case, the concat layer merges tensors from two different stages: the previous layer, stage 11, and stage 6 from the backbone. This fusion helps retain both high-level contextual information and lower-level spatial details, improving the model's ability to detect objects across various scales. With that, we have covered all the unique building blocks of YOLO11's architecture, except for the detect class, which is where we are heading next. As we make our way to the detect class, let's move quickly through these already familiar modules that we have previously covered. Next, we progress to another C3K2 false module, where we can also visualize some of its feature maps. Following that, we apply another upsample layer, as well as another concat layer. These layers play a crucial role in preserving and merging spatial information, ensuring that key features extracted earlier in the network remain accessible for object detection. Next, we encounter another C3K2 false module, which further refines feature representations by processing the concatenated features from the previous layers. We can see the generated feature maps here. The output of this block will be the first of 3 tensor inputs to the detect class. This tensor, with spatial dimensions of 60 by 80, primarily captures small-scale features, making it well suited for detecting objects smaller than 32 by 32 pixels. This tensor is also fed into a convolutional block, producing additional feature maps, which we can visualize here, further refining the extracted features while slightly reducing the spatial resolution. The output then passes through another concat layer, where it is combined with the tensor from stage 13. The result of this concat operation is passed to another C3K2 false block, which continues feature processing, reinforcing spatial and contextual relationships between layers. This resulting tensor serves as the second input to the detect class. This tensor, with spatial dimensions of 30 by 40, primarily encodes medium-scale features, making it ideal for detecting objects ranging from 32 by 32 to around 100 by 100 pixels. This tensor then undergoes another convolutional block, further reducing its spatial resolution. The output is concatenated one last time, in this case with the output from the C2PSA block that we examined earlier. Finally, this tensor is fed into our last C3K2 true module. The resulting feature maps, now at a 15 by 20 resolution, are optimized for detecting large objects, typically those spanning more than 100 by 100 pixels in the input image. At this point, we should be proud. We've successfully navigated through the entire architecture, arriving at the final and most critical stage, the detection head.